Hello everyone, welcome to the OneClass channel. My name is Marlyn. I'm a second year student at the University of Waterloo, studying chemical physics with a minor in math. Today I'm going to be walking us through some high school level and college level chemistry problems. I'm going to be focused on Lewis structures today. Be sure to check out the links in the description if you're in need of any extra homework help or would like some one-on-one tutoring. So for our first one, we are trying to find out whether CH2Cl2 will be polar or non-polar. So for all of our questions today, we will first be counting the valence electrons. We need to count the valence electrons. Secondly, we will be checking out our formal charges. I'll explain why later. Third, we'll figure out its VSEPR theory, and then for the fourth part we'll be figuring out the net dipole moment. Okay, so for this one, as I said, let us begin with the valence electrons. So I have CH2Cl2. For my valence electrons, I have C, which is contributing 4 valence electrons per carbon, hydrogen, which is contributing 1 valence electron per hydrogen, and chlorine, that is contributing 7 valence electrons per chlorine. So for these ones, I multiplied it by 2 because I have 2 chlorines and I have 2 hydrogens. All of this is going to give me 4 plus 2 plus 14. And that's going to give me a total of 20 electrons to place. Okay, so let's go about doing that. So we need to pick our center, and we will typically be choosing the electropositive. Let me just write that out. Species. And the reasoning for this is because they tend to be able to make more bonds. While keeping formal charge low. This makes sense because they're electropositive because they like electrons. They lack electrons. They tend to be towards the left of the periodic table, and so they tend to be able to make the most bonds without messing up their formal charge. And so in this case, of course, we can't put in hydrogen, so we're going to put in carbon as our central, and then we can just place 4 bonds around it and just place the hydrogen and the chlorine. Okay, we can double check all of our electrons. 2, 4, 6, 8. So right now I have 12 electrons left over. I can fill in all of chlorine's octets, and that would now give me a count of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So all of my valence electrons are now taken care of. Okay, next up, as I said up here, we want to check out the formal charge. Now, the reason why we want to check out the formal charge is so that we can minimize it, because when they typically ask you for the Lewis structure, they're asking you for the lowest energy Lewis structure, and the universe doesn't like high charges separated and just large charge separation distances, and so we can deal with that by taking account of this formal charge, and if we minimize it, we're therefore minimizing the energy of the structure. So let's check our formal charges. Let me just write out the formula for you. So the formal charge will be the valence electrons minus the number of sigma bonds minus the number of lone electrons. So why I say sigma bonds is because when you really think about it, like for example, if I'm trying to do the formal charge of carbon, just as a quick example, for carbon, I have 4 valence electrons. Now, when I say sigma bonds, I'm talking about the electrons that it's contributing to each of these bonds. So here, carbon has made 4 bonds, so it's contributing 1 electron to each, so 1 by 4, which is 4, and then it has no lone electrons, and so its formal charge would be 0. For hydrogen, let's just do the same thing. For each of them, they all have 1 valence electron and are contributing 1 valence electron to the bond that they're making with the carbon, giving me another formal charge of 0. And lastly, on the chlorine, I have 7 valence electrons minus, they both have 1 bond, so 1 electron contributed to the sigma bond with carbon, and they both have 6 lone pairs of electrons, so giving me a formal charge of 0. So I can see that, well, first off, I would like to get the net formal charge to equal that of the molecule. So all of the charges add up to 0. The molecule has a net charge of 0, so I can tell that this is correct. And next up, I would like to minimize them. And I've done so, they're all 0. I can't minimize them any further. And so this is the best structure, is what that has confirmed. I've taken account of my valence electrons, I've taken account of my formal charge, so everything is good to go. So next up, I need to move on to the Vesper theory. So the Lewis structure just gave me the Lewis structure method is great for electron bookkeeping. That's why we do it first, to figure out whether it's polar or non-polar. I need to figure out where my electrons are going, where they would best be placed to minimize charge separation and to ensure that all of the valence electrons are taken care of. And so now I move to the next step, and that's Vesper theory, which is figuring out its actual geometry. So to do that, I first need to count the number of terminal groups on my central atom. I have 4, and none are lone pairs. So that notation is A for my central atom, X for the number of bonded groups, and I have 4 bonded groups. If for whatever reason, let's say I didn't have 4 bonded groups, instead I had 3 bonded groups in a lone pair, I'd write AX3 for the 3 bonded pairs, E1 for the 1 lone pair. So in this case, I have AX4 as we've just discussed. Okay, and so what that means is when I pull up my Vesper chart, this is called the steric number. Okay, so now that I have AX4, I can already tell you the electron geometry and the molecular geometry. So in this case, I'm lucky, they are both the exact same. The electron geometry is the way electrons are generally organized around the central atom. And so whether I have lone pairs or bonded pairs, it doesn't really matter. I have 4 pairs of electrons organized around my central atom. And so when I look for the electron geometry, I'm looking for the one that is telling me I have 4 groups of electrons arranged. And so I just come to 4, and it's the first one. I'm not accounting for which ones are lone pairs, which ones are bonding pairs. I'm talking about electrons generally. And so my electron geometry will be tetrahedral. Now, molecular geometry accounts for which ones are lone pairs and which ones are bonding pairs, because when you're talking about the molecule, you're talking about CH4. You're not thinking or talking about the lone pairs, you're talking about the atoms you have. So it's the way the atoms are arranged, not including those lone pairs. And so I would now move left according to however many lone pairs I have. This time, as I said, I have 0 lone pairs, so the electron geometry matches my molecular geometry, and so it will also be tetrahedral. Okay, now next up, I would like to draw it out. And so, yes, there are many ways that you can decide to place the hydrogens and carbons, which is something you must have wondered. I could decide to place, the hydrogen and chlorines. I could decide to switch them. I can decide to have the chlorines across from each other. Any of those would really be acceptable. It won't change the ultimate result. And so when I draw it, let's place Cl here, have a Cl coming out, a hydrogen, and a hydrogen going up. Alternatively, let's say I didn't have that, instead I had this configuration. I'll show you in just one moment that it makes no difference. Okay, now let's begin thinking about our dipoles. So remember that our dipoles needs to point from the electropositive center to the electronegative one. Okay, and so between carbon and hydrogen, you can pull up a chart of electronegativities. You don't need to memorize any of the electronegativities. You just need to remember where things are relative to each other, which is super duper easy. Electronegativity increases going up on the periodic table and towards fluorine. Fluorine is the most electronegative one. And so if you just keep that in mind, hydrogen is yes up, but completely to the left. And so carbon is of course going to be more electronegative. Now between carbon and chlorine, chlorine is a little bit lower, but it is to the left more than carbon, and so it's going to be more electronegative. And with electronegativity, I don't only need to take care of the direction of the dipole, but the magnitude of the dipole, which means that when I'm talking about hydrogen compared to carbon versus carbon compared to chlorine, those two dipoles are going to have different magnitudes because they're representing differences in electronegativity. And so I'll draw it in a different color just to remind myself of that when I'm trying to cancel things out. And so even if I had it here, I'd have this coming out, this pointing in, and this pointing in. So already I can see that these dipoles won't cancel each other when I do add them up. These two will yield a dipole pointing downwards. And these two, we have one pointing downwards and one pointing slightly upwards. And so they will add in a different way, but it's not going to add to a dipole that can cancel this one out. So I can already tell that this one's dipole moment is non-zero. Write it out as net mu is not equal to 0. And same thing here, these ones will add up to yield a vector pointing upwards. These ones will slightly cancel, but not all the way because of this one's angular component. There's no way those two remaining vectors can cancel. And so again, my net dipole moment here will be non-zero. So as I said, no matter how you arrange the chlorines and the hydrogens around my carbon, the dipoles will not cancel. And so overall, I will get that CH2Cl2 is a polar molecule. Okay, and that's it for this question. Okay, next up I'm dealing with the Lewis structure for BrO2-. I would like to indicate the formal charges on my bromines and oxygen atoms, and then answer the following questions, indicate my number of valence electrons. So let's just write that out. So first I would like my Lewis structure with my formal charges indicated. The second part, I would like to indicate the number of valence electrons. For the third part, I would like to know my preferred Lewis structure. D, how many resonance structures do I have? So we'll talk about this a little bit. And E, what is the shape of my ion, the name of my ion too. So this will relate to VSEPR theory. Let's just do that super duper quickly. The way that this question is ordered, I'm going to answer B in C. Answering B and C will give me the answer of A. And so I need to count my valence electrons, as I said. So bromine is going to give me, try it out a little bit better. So I have bromine, I have O2, and I have a minus. So remember, minus charges mean that, so a neutral charge would mean that my number of protons equals my number of electrons, and the two cancel perfectly, yielding a net charge of 0. But a minus charge means that I have an extra electron compared to the number of protons that I have. So it means when I'm counting the valence electrons, I'm going to need to add that extra electron, which is why I need to keep note of the charge. So bromine gives me 7 valence electrons for every bromine atom. Oxygen gives me 6 valence electrons for every oxygen atom. And the charge is going to give me 1 valence electron per negative charge. And so that is going to give me 7 plus 12 plus 1. And that's 20 electrons to organize. Okay. Now I need to decide on my central atom. I can already see I have 1 bromine, 2 oxygens. It doesn't make sense for oxygen to be my central atom. It makes more sense for bromine to be my central atom, as there's more symmetry in that, and chemistry loves symmetry. So let's go ahead and put bromine right in the middle, and I'll put 1 bond to each oxygen. We can fill in everybody's octets and see what will be left over. Okay, so with this configuration, I have 6 by 2 on lone pairs on each of the oxygens, plus 4 lone pairs on my bromine, plus 4 in the 2 bonds. And so that's going to give me 8 plus 12, which is indeed 20 electrons. So yes, my 20 valence electrons have been taken care of, but this is where the formal charge becomes very, very important. As I said in the previous question, Lewis structures provide a method of electron bookkeeping, which is very, very important in quick determination of what the structure should look like. If it has a valid Lewis structure, the molecule should exist. And so even though it's completely empirically based with no basis in what is happening down on the level of quantum theory, it works very, very well for doing things quickly when you need to figure out whether something is plausible. And so let's check our formal charges. And I know that I'd need to minimize my formal charges and minimize charge separation if I want this to be a low energy molecule. And typically when you ask for the Lewis structure, you want the lowest energy. And so for each of my oxygens, I have 6 valence electrons minus the 6 lone pairs minus the 1 they have each contributed to a bond. So this gives me a total charge of negative on both of them. And on my bromine, I have 7 valence electrons minus the 4 in lone pairs minus the 2 in bonding pairs, and that is going to give me positive 1. So I'm going to have 1 positive. And so, yes, I see that the net is correct. I have a net of -1, but my charge separation is not optimal in this case. I can minimize the charge on 2 of these and just leave a minus on 1 of them. That makes the most sense, and that would be energetically favorable. And so instead of having this, I'm going to move around some electrons and try and minimize the formal charge just a little bit more. So I know oxygen likes to have 2 bonds and bromine likes to have 1. So let's give one of the oxygens the 2 bonds and take away a lone pair on the bromine. That will leave me with that. Now I have 2, 4, 6, 8, 10, 12, 14, 16, 18. So I still have 2 more electrons. Let's just put them back on the bromine. Okay, and so now that I have this, again, let's count our formal charges. We'll call this oxygen 1 and oxygen 2. On oxygen 1, I have 6 valence electrons minus the 4 in lone pairs minus the 1, 2, 2 in bonding pairs. And so that's going to give me a net formal charge of 0. On the bromine, I have 7 valence electrons minus the 4 in lone pairs minus the 3 in bonding pairs, giving me 0. So great, I've minimized the charge on 2 of them. And on oxygen 2, I'm going to have 7 minus 6. Sorry, 6. My apologies. I have 6 valence electrons minus the 6 in lone pairs minus the 1 it has in this bonding pair. And that's going to give me minus 1. And so that is what I'm going to be left with. Now I've minimized the formal charges and the charge separation, which is great. And I have the net formal charge adding up to what I want it to add up to. And so I can come back up here and answer some of these questions. We find I have 20 valence electrons. Okay. Now, next up, we need to discuss this concept of resonance structure. So now that I have my valid Lewis structure, resonance structures are any other valid Lewis structures. And why this is important is, so the Lewis structures assume that that electrons are either localized in lone pairs or bonding pairs. We know from quantum theory that is not true. Electrons can go wherever they want as long as it is energetically permitted by Schrödinger's equation. And so we need to factor that into what we have, and we can do that by writing down resonance structures that help delocalize these electrons. Why delocalization is preferred is because when electrons are delocalized, it minimizes their interaction with each other, and that minimizes the charge. Delocalization is good for minimizing the charge, and we always want to, not minimizing the charge, for minimizing electron-electron interactions, and we always want to do that because that will minimize the energy of our molecule. And so, are there any other ways that I can place the electrons and have a different Lewis structure, but that is permitted? And so, I can see that rather than having the 2 bonding pairs here, I can move one bonding pair back to the oxygen, right? Move this bonding pair onto bromine, and move one of these lone pairs onto this. And so just so you know, a double-headed arrow means I am moving both electrons. It is heterolytic. And a single arrow means that I am moving one electron, which is homolytic. And so when I do this, I'll end up with a second structure, which looks basically like this reflected in a mirror. And so they're not separate structures, they're the same wave function when you actually think about it, but with electrons arranged in a different way, which factors in that delocalization of electrons. And so now, instead I have this, the number of my electrons has not changed, and so I still have my 20, and now the minus charge is going to be here instead. And so I can come back up here and say that I have 2 resonance structures. Okay, now I need to, so these are the 2 preferred Lewis structures, equally preferred because you see the symmetry in it, so none has a higher weighting on the wave function than the other. And so now we figure out the shape of the ion. And so I need to go to Vesper theory. I need to figure out how many terminal groups I have on my central atom. And so for both bromines, I have 2 lone pairs acting as groups, and I have 2 oxygens acting as groups. And so I have 4 groups, and for its notation it will be AX2, E2. So 2 bonding pairs, 2 lone pairs. And so now when I come to my Vesper chart, I can quickly tell that the electron geometry, it won't account for which ones are lone pairs, which ones are bonding pairs, so I just go straight to a steric number of 4, and my electron geometry is going to be tetrahedral. For my molecular geometry, I now account for which ones are lone pairs, which ones are bonding pairs, and I'll find that this is actually going to be a bent shape. So I just come to 4, and I go right to 2 lone pairs, so that is bent. And so now when I draw it out, you can draw it both, or you can use the broken lines to show that the bonds are delocalized, depending on what your instructor would like. And so we're just going to draw both. So I have Br, oxygen, oxygen, and then I have my 2 lone pairs. Okay, and don't forget your minus charge. So those will be my 2 Vespers, right? Just one moment. Okay, so now that I have that, I'm going to scroll right back up. So the shape of the ion is going to be bent. And lastly, we need to figure out the name of the ion. So for my essential atom is bromine. And I have I have 2 of them with 1 minus charge. And so this is di for the 2, ox for the oxygen, and ide to factor in that one of them is an ion. And so this will form bromine dioxide would be the name. And that's going to be it for this question. Okay. Next up, we have the ammonium ion, and I'd like its Lewis structure, so I'm going to count its valence electrons. I have 4 from, let's just write that out a little better. I have nitrogen, H4, and a plus charge. So again, the charge would be neutral if the number of protons equals the number of electrons. A positive charge means I have extra protons, and so it's going to be -1 valence electron is how I'm going to account for that. And so nitrogen are going to give me 5 for every nitrogen, so 5 valence electrons per atom. Hydrogen is going to give me 1 valence electron per atom, and the positive charge is going to be -1. So when I add that all up, I'll get 5 plus 4 minus 1, which is 8 electrons. Now, which one will I place as my central atom? Nitrogen can make more bonds. It doesn't make sense to have hydrogen as my central atom. It only has space for 1 bond. And so nitrogen, and I'm just going to put my hydrogens around it. That makes the most sense. Do I have any more electrons to place? 2, 4, 6, 8. So all of the valence electrons are taken care of. Nitrogen's octet is full, and hydrogen has as many electrons as it can have. And so let me just check my formal charge now. My formal charge on the nitrogen will be 5 minus the 4 electrons it has in each. It has 1 electron in each bonding pair. By 4, that's 4. And so I have a +1 charge because it has no lone pairs. Hydrogen, I have 1 valence electron minus the 1 valence electron it has in each bond. And so that is going to give me 0. So I have a positive charge on my nitrogen. And that is going to be it for this one. Okay, next up, I would like to draw the Lewis structures of the following species and give the additional information that is asked for. And so, let's do part A first. So I have SO3. Okay, so as usual, I need to count my valence electrons. I will have S and O3. So S will give me 6 per atom, and oxygen will give me 6 per atom. And so this will all add up to 24 electrons to distribute. Okay, so which one should I place as my central atom? I have 3 oxygens, 1 S, sulfur, and so it makes the most sense to place sulfur as a central atom. And then let's put a single bond to each oxygen. Let's fill in our octets. Okay, and now let's check. We have 6 by 3 because of each of the lone pairs on each oxygen, plus 2 by 3 because of the bonding pairs, plus 2. That's going to give me 18 plus 6 plus 2. And that is 24 plus 2, which is 26. I have too many electrons. And so I'm going to get rid of this lone pair on the sulfur. And that will leave me with the desired 24. Now let me check on my formal charge. On the sulfur, I will have 6 minus 3 minus 0. So that gives me a large formal charge of plus 3. On each of the oxygens, I will have I will have 6 minus 6 minus 1, giving me minus 1. But then I have 3 oxygens, so that gives me a minus 3 charge in total. So I have minus, 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 plus 3. The net does add up to what it's supposed to be, which is 0. But I have too many charges, and that increases the energy of the molecule to be much higher than it needs to be. And when you ask for the lowest structure, typically ask for the lowest energy lowest structure. And so this is not an ideal structure. Its energy is too high. And so how I can deal with this is, first I need to check the periodic table and check, can sulfur take an expanded octet? And so let's just one up. Okay, so can sulfur take an expanded octet? And it can. And so instead of having single bonds, I'll have double bonds, and that's how I'm going to minimize those charges. And so I'm going to give each oxygen the double bond it would like. Okay, and so now let's ensure the electrons make sense in terms of octets. Ensure I do have the correct number of valence electrons, because I've gone back to the start practically. And so I have 2 by 6 plus 4 by 3. Yeah, and that's going to give me 12 plus 12, which is 24. So my valence electrons are now all accounted for. Now let's double check on that formal charge. On each of the oxygens, I have 6 minus 4 minus 2. 6 valence electrons minus the 4 lone pair electrons minus the 2 it has 1 electron in each bonding pair, so that totals to 2. So 0 on all of them. And on my sulfur, I have 6 minus, it has a single electron in each of the bonding pairs, so that's 6, giving me 0. And so the net adds to what it's supposed to be, and I've minimized it, which was the point. And so this is going to be my best Lewis structure. And now I need to determine whether it's going to be polar or non-polar. So let's go about doing that. So first I count its steric number, and that is the number of groups on my central atom. I have 3 groups, so that's 3. And the notation will be AX3. There's no E, so you can write E0, doesn't really make a difference, just write AX3 would be best. And so now I go ahead, check my VSEPR chart. My electron geometry will be trigonal planar. And so my molecular geometry, since I don't have any lone pairs. And so when I draw it, it will look exactly as it did before, because I was informed when I drew it. And that's what it's going to look like. Now I can double check on my dipoles. Oxygen is more electronegative, and so that's going to go that way, that's going to go that way, and that's going to go that way. These two will add to give you an equal vector pointing down, and they will all cancel, and so it's going to be non-polar. Okay, on to our next one. For A, it is non-polar. For our next one, we have PF3. So as we did before, count your valence electrons. So I have PF3. Each phosphorus will give me 5 per atom, and each fluorine will give me 7 per atom. This will add to a total of 21 plus 5, so I have 26 electrons to distribute. Let's put phosphorus in the middle. Fluorine is the most electronegative. It doesn't make sense to have it in the middle. And so let's start with that and fill in everybody's octets. And then see if you have anything left over. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So all of my electrons are taken care of. Now let's go on to check my formal charges. On each of the fluorines, I have 7 valence electrons minus the 6 it has in lone pairs minus the 1 it has in each bonding pair. And that is going to give me a formal charge of 0. On my phosphorus, I have 5 minus the 3 it has in bonding pairs minus the 2 it has in lone pairs, and that is also going to give me 0. And so my net is correct, and it has indeed been minimized. I can't minimize it past 0. So that is going to be my best Lewis structure. And so as usual, I go about finding the steric number now. How many groups do I have on my central atom? And I have 3 bonding pairs plus the 1 lone pair. And so that is going to give me 4. Its notation will be AX3 because I have 3 bonding pairs, E1 for the 1 lone pair. So now when I go to its Vesper chart, I'll look for its electron geometry and its molecular geometry. So as I said, electron geometry doesn't care which ones are lone pairs, which ones are bonding pairs. They're all pairs. It just cares about the way electrons are organized. That's why it's called the electron geometry. And so my electron geometry will be tetrahedral. The electrons are organized in a tetrahedral fashion around my central atom. Now, my molecular geometry cares about the way my atoms are arranged around my central atom, and they're arranged in a trigonal pyramid fashion. So I account for the fact that I have 1 lone pair. Okay, now, just so you know, from this point already, I can tell that it's polar, and the reasoning why is because lone pairs of electrons on my central atom or different atoms mess up the symmetry. A lack of symmetry means that the dipole moments will not cancel, and that means that I will have a non-zero dipole moment. So you don't even need to draw it oftentimes to figure that out if you're trying to be quick, but just for the sake of it, let's draw it. And so I'm gonna have a fluorine here, fluorine here, fluorine here, and then I will have my lone pair going up. Let's fill in everybody's octets. Okay, now we do our dipoles. Fluorine is more electronegative. And then I have a dipole going up because lone pairs are always more electronegative, and they're also destabilizing the angles between the bonds because of the extra repulsion. And so additionally, this dipole will have a different magnitude, and so obviously these 3 won't cancel. The 3 fluorines will add up to a vector pointing down, and then I have a different vector pointing up. So these 2 different magnitude, opposite direction, they will not cancel. And so my net dipole moment is 0. And so that means, sorry, is not 0. And so this molecule will be polar. Let's just go ahead and add that up here. Okay, now for the next one. I have F3SiH. So as usual, let's go about counting our valence electrons. F3SiH. So fluorine gives me 7 valence electrons per atom. Silicon is going to give me 4 valence electrons per atom. Hydrogen is going to give me 1 valence electron per atom. This all adds up to 21 plus 5 again, and that's going to give me 26 electrons to arrange. So I now need to pick my central atom. Fluorine is the most electronegative. It can only make 1 bond, so it doesn't make sense to have that as a central atom. Hydrogen is not as electronegative, but it only has space for 1 bond because it only has the 1s orbital. And so my best choice will be silicon. It's like carbon as it can make 4 bonds. And so let's go ahead and place that. Let's place my 3 fluorines and my 1 hydrogen. So again, as you're doing chemistry, always look at the symmetry. It will tell you things ahead of time. I can already tell that this is not symmetrical. I have 3 fluorines and 1 hydrogen on one side, so those dipole moments won't cancel. I can tell you that right now. But let's go ahead and do it all out so that you can see it. So always try and make a solid prediction on where things should go with your question, and that makes things easier because you learn to look for patterns in the question that will speed up how fast you answer it, and you'll have more confidence in yourself as you learn that your assumptions are oftentimes correct. And so I fill in my octets on the fluorines, and that will leave me with 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. All of my valence electrons are taken care of. Let's go ahead and check my formal charges. On silicon, I'm going to have 4 valence electrons minus the 4 it has, because it has 1 in each bonding pair, and that's going to give me 0. On the fluorine, I'm going to have 7 valence electrons minus the 6 in the lone pairs minus the 1 in each bonding pair, 0. And on my hydrogen, I have 1 valence electron minus the 1 valence electron it's contributing to this bond, and that's going to give me 0 too. And so my net adds up to 0, as it should, and it has been minimized. And so this is going to be my best structure. Now I go on to my Vesper theory. I need to find my steric number. So figure out how many terminal groups I have on my central atom. I have 4 bonding pairs. Its notation will be AX4. And that means that when I pull up the chart, my electron geometry is going to be tetrahedral. And so my molecular geometry, because I don't have any lone pairs. So just go to steric number of 4, 0 lone pairs, tetrahedral, tetrahedral. So, now let's go about drawing that. Okay, and then let's do our dipoles. Fluorine is the most electronegative, and silicon is more electronegative than hydrogen. But the dipole magnitude is going to be different, so let's put it in blue. And so obviously I can see there's no symmetry in the way that these dipoles are pointing, so when I add them, they're not going to cancel, which is what I said initially. And so it will lead you to a net dipole moment that is non-zero. And so again, I have a polar molecule. Okay. Now let's do D and E. So for D, I have SiH3 minus. So as usual, begin with your valence electrons. I have silicon, I have H3, and remember, a minus charge means I have an extra electron that is making it no longer neutral. And so for my silicon, I have 4 electrons per atom. For my hydrogen, I have 1 electron per atom. And my plus charge gives me +1 on the electrons. And so that's going to lead me to 4 + 4, which is 8 electrons to distribute. Silicon makes the most sense as my central atom. I can't have hydrogen. Place the hydrogens around it. This gives me 2, 4, 6. I have 2 more electrons. Makes the most sense to fill silicon's octet. And so that's what I'll have. Now, check my formal charges. On my hydrogens, it is 1 minus 1, giving me 0. On my silicon, I have 4 minus 3 minus 2, giving me that -1 charge that I was looking for. The net adds to what it's supposed to be, and it is indeed minimized. Hence, this is going to be my best Lewis structure. Now I go about drawing its Vesper. Again, let me just look at it and make a guess on what my answer is going to be. I see a lack of symmetry that is very, very clear. I have 1 lone pair, like it did previously with B. That's going to destabilize things a little bit and lead you to a non-zero dipole moment. The dipole will not cancel with the other hydrogens. Now let's go ahead and do it, see if that guess was correct. So my steric number, I count the number of electron groups I have around my silicon. I have 3 in bonding pairs plus 1 in a lone pair. So I have a steric number of 4. Its notation will be AX3E1. 3 bonding pairs, 1 lone pair. My electron geometry will only account for how many groups I have, not which ones are atoms or electrons, and so my electron geometry is going to be tetrahedral. My molecular geometry is only looking at the way that the atoms are arranged around my central atom, and that is going to be trigonal pyramid. So let's go ahead and draw that. And I'll have silicon, my 2 lone pairs, and all of my hydrogens. Okay, so already my lone pairs are more electronegative. And then I have silicon more electronegative height for all of these. And so these 3 add to a vector pointing up. And we have the vector already pointing up for the lone pair. These obviously will not cancel, and so my net dipole moment is non-zero. And again, I will have a polar molecule. And that's going to be it. So D is going to be polar. Now for our last one. And just a few tips for chemistry and those who will be taking it and are in high school right now and wish to take it in university. Yes, in high school they teach you a lot of these rules that you get used to relying on and you can memorize, but in university you can't do that because you need to think through it and understand what's actually happening, because those rules are given to you at the high school level, so you don't have to think about what is going on down on the level of electrons, so quantum mechanically. That's why you have so many exceptions to these rules, and those exceptions are because of what is going on. And so in university, when you actually do know what's happening, you need to be able to think through it and explain those exceptions oftentimes, like with ionization potentials and atomic radius and all of the above. So for our last one, we have Br2CH2. So count your valence electrons. Br2CH2, I have no charge. Br contributes 7 valence electrons per atom. Carbon, 4 valence electrons per atom. Hydrogen, 1 valence electron per atom. That is 14 plus 4 plus 2, and that is going to give me 20 electrons. Okay, now choose my central atom. Carbon can make the most bonds, so I'll have carbon in the middle, and I'll just have 4 bonds attached to it and arrange my atoms in any way I like. I can put the 2 bromines next to each other. You'll see that it doesn't matter. There's still going to be a lack of symmetry in the dipole moments because of their magnitudes, and so I'll just go with this one for now. Check my formal charges. On each of the hydrogens, I have 1 minus 1, 0. On my bromines, I will have 7 minus 6 minus 1, 0. And on my carbon, I will have 4 minus 4, 0. So the net is as it should be, and the charges have been minimized. So I didn't check if my valence electrons are correct. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So they are. So this is going to be my best Lewis structure. Now I go about its Vesper theory. How many groups do I have attached to my central atom? I have 4 in bonding pairs and 0 in lone pairs, so my notation will be AX4. My electron geometry talks about the way that my electrons are going to be arranged. And so it will be tetrahedral. And my molecular geometry talks about the way the atoms are arranged, and they're also arranged in a tetrahedral fashion because I don't have any lone pairs. So let's go ahead and draw that out. I have C. I'll put the bromine right here. Hydrogen, bromine, hydrogen. Okay, now I'll go about drawing my dipoles. Bromine is more electronegative. Hydrogen is less electronegative. And let's see for that last bromine. And so again, lack of symmetry. This is not pointing down, it's pointing towards you. And so it'll tilt, when it adds to this one, it'll tilt it a little bit and reduce its magnitude upwards just a little bit. So I'll have a net vector roughly pointing up. And for my 2 hydrogens, their angular component will cancel and give me a net vector also pointing up of different magnitude. These two obviously cannot cancel each other out, and so I will have a net dipole moment that is non-zero, and so I have a polar molecule again. And so these are all of my answers. Okay, and those are all of the questions I have for you today. I hope you enjoyed today's Q&A session. If you'd like to be notified of when we do post on the channel again, be sure to hit the subscribe button and the bell next to it so you can get the push notification. If you'd like to post questions of your own, be sure to check out the links in the description, as it'll give you access to the OneClass page where we do source our questions. This has been Marlyn from OneClass, and I hope to see you next time.